Hello all, I'm John Pinkham, a second-year graduate research assistant at the University of Maine. The focusing goal of my research is the development of live load distribution factors for GBeam highway bridges. The GBeam is used to date in 4 bridges, including 2 in Hamden, Maine, 1 in Florida, and 1 in Rhode Island, with others in design. So the GBeam, a little bit of background on it, it's an open box girder made from a vacuum-infused fiber reinforced polymer, or FRP, that incorporates both glass and carbon fiber in a complex architecture where the materials usage is optimized. So the GBeam can be cast with act compositely with a concrete deck that's cast over it, which can be reinforced with either steel or FRP rebar. A typical girder cross section can be seen in the bottom left in Figure 1. That's one for Hamden Gristmill Bridge, which will be talked about here in a second. So the GBeam was developed to be a direct replacement of concrete and steel girders, but it's going to offer higher corrosion resistance, a lighter weight material, and longer lifespans in comparison to steel and concrete. And that's what makes it something that we really like. So with any new technology, there's unfamiliarity, and many like to stick with what they've designed with in the past. And for most in the bridge world, that's typically been steel and concrete. So how do we encourage people to start designing with a new material of FRP, such as the GBeam? So developing a design guideline that people can look to in the process of designing will be important. And in that, assessing and developing live load distribution factors is going to be important. So the importance of live load distribution factors is that helps quantify the amount of load applied to a single girder. So then the girder can therefore be designed for as a single beam. And both shear and moment are something that need to be quantified in this process. So the research plan, it can be broken down into 5 steps. Those 5 steps include step 1, where you live load test constructed bridges. As mentioned, there's 2 in Hamden. Those are close to the university. Those were tested, and that is complete. Step 2 is create finite element models of both of those Hamden bridges. And that is also complete. And then step 3 is using the finite element models of those bridges and calibrating them to the test results from task 1 and really understanding the bridge behavior. And then step 4 is, can we create a suite of FE models for a parametric study where we look at changing spacing, span length, different parameters that we think are going to affect live load distribution, and change that in a model so it looks at multiple different bridge geometries and then loads it under multiple different AASHTO loading cases. And then step 5 is to take the results of that parametric study and develop live load distribution factor equations that can be used in future design. So the current design practice is to use live load distribution factors for a type C concrete box girder, which is provided in the AASHTO guidelines. And the first bridge to be constructed using the GBeam was in Hamden, Maine, and referred to as Hamden Gristmill Bridge. So Hamden Gristmill Bridge has been live load tested, as mentioned, multiple times, and it was laid up, tested with longitudinal strains being measured during the test, and using those, you can infer girder lane fractions. So just assessing what fraction of the load went to a single girder, and then those are tracked in table 1 at the bottom center. So in table 1, it's comparing the girder lane fractions inferred for the maximized moment cases under 2 lanes of loading, and then comparing it to the distribution factors calculated using AASHTO. So as can be seen, there is some differences between the AASHTO predicted distribution and what was measured during the test. Specifically in girder 1, where there's a sidewalk and it's on the exterior, there's up to an 82% difference visible in that girder. But then on the interior, it's doing a little bit better job, where the maximum girder lane fraction measured in the test is only 1% below the maximum distribution factor for an interior girder predicted by AASHTO. So on the interior, it's doing a little better. But this shows how important it is to perform the research to quantify live load distribution factors that are specific to the GBeam. So table 1 only compares moment distribution. However, shear distribution is also something that needs to be looked at and important. And 2 tests were completed in the summer of 2023 that really aimed to assess shear distribution in both of the constructed Hamden bridges, Hamden Gristmill, and then another referred to as Twin Bridge. And those tests, again, were really focused on shear distribution. Now, something we want to be looking at with shear distribution is not just the distribution to each girder, but within each girder, as discussed in the geometry, there's 2 webs, and we need to track and assess what kind of distribution of the shear goes between the 2 webs in a single girder. So one might assume that the distribution between the webs is going to be equal, but as seen in figure 2 here, in a single girder, this is girder 3, so it's a center girder on Hamden Gristmill. And under a extreme shear loading case, the maximum produced shear during the test, we see that there's 150 microstrain difference of the shear strains between one web and the other within that girder. That is going to represent more than 1.5 times as much shear from one web to the other. So an assumption of equal shear distribution between the webs does not appear to be valid. So that's something that also needs to be looked at and assessed within any distribution factors in the future. Now, if you also look to this bottom there in the center, figure 3 is going to be showing a snapshot of the two of the different modeling approaches used for Hamden Gristmill Bridge. So on the left is a high fidelity model, is what we call it. That's going to incorporate multiple components of the bridge. We used it for calibration. And then the simplified version is on the right, which is going to be used for the, as mentioned, the suite of FE models for the parameter study. So the high fidelity model is incorporating not just the girders and deck, but the sidewalk curb, diaphragm, railings. It's very sophisticated, has multiple components. And then the simplified model is including the girders and the deck, and that's basically what's there. And the girders in this simplified model, which was looked at for assessing moment, has the girders as beam lime elements, doesn't incorporate the true geometry and have this 2 webs like is actually present with the girders. And that's something to keep in mind. But what's the importance of having 2 different models? So the high fidelity model, we can calibrate to the test results, look at the bridge behavior, not just of the live load distribution, but basically anything we really want. We can look at what's going on and have a better understanding of the bridge behavior. And then the simplified model, that's something that is more generalized, has less attributes to it, is going to run analyses faster, and then it's easier for us to edit the parameters such as spacing, span, and then use that for a suite of FE models and developing live load distribution factors. And we can also run that in a much faster time. Now, the results of using the calibrated high fidelity model and simplified model show that they both accurately predict moment live load distribution in the heaviest loaded girders, as seen in figure 4 to the right, where the test results match up well in those heaviest loaded girders. Girders 3 and 4, you can see that the model predicted distribution is very similar to what was measured in the field. But then one aspect is mentioned is that might be good for moment, but that simplified model there is not capturing the 2 webs that the girders actually have. So you can't assess that differential shear strain measurement as seen in the fields in figure 2. So moving forward, we're going to be looking into another simplified model for assessing shear distribution, where we can also look at the shear strain distribution between the webs and finding a simplified modeling approach where we can not only get the shear distribution to girders, but also the shear distribution between the webs in a girder. And that's where the research is headed. And then after we have those simplified models, we run them through the suite of parameter study and then develop the live load distribution factor equations. So that's where the research is headed. That's the end goal. And I'd like to thank all those who have helped along the way so far in this research. That would include the Maine DOT, AIT Bridges, some colleagues here at the university, Andrew Skank, Keith Barabee, Jake Bear, and my advisor, Bill Davids, as well as TIDC and UTC programs for providing me with the resources and ability to perform this research. Thank you all for listening.